Hi, I guess we should get started. Before I start, just remind you that homework 3 has been released, and then the solution key, the homework 1 has been released as well. So you can check them out, and homework 2 solution will be released once the TA grade everything, and then I will release them. So homework 3 is still by the end of next Friday. So you still have like 10 days or so to get it done. So last class, we basically finished this sampling distribution. So today we'll talk about estimation. But since the foundation of the estimation is this one, so we will try to quickly review what we have done so far. So this is the beginning point of we use data to do analysis, okay? And we start with what we call simple random sample, where each element in the population will be chosen with the same probability, and if they're being chosen, then each element is chosen random independently. So choosing one doesn't affect the choice of the others, okay? So the easiest way to think about this is when you see simple random sample, is the mean and the variance will be same as the population, okay? And the covariance will be dependent, right, with 0, and then they're independent. And for our class, we would focus on mainly the sample mean, okay? Because this is the way to estimate the population mean mu, which is something we care for. And of course, we also care the sigma square, which today we will talk about is we will try to estimate that based on the sample variance, okay, S square. Okay, we will talk about this more very soon. But the main thing we want to look at is sample mean. That is the central thing we want to look at. And that's why the rest of this topic is based on looking at the different property of the sample mean, right? So the first thing we learn is the expectation of the sample mean, right? Which is will be actually, right, we actually learned that. Oh, I haven't shared the screen yet. Okay, which we learned the property of the sample mean will be, one of them is expectation, that's actually equal to mu, right? And the variance will be equal to sigma square over n, okay? And this actually signal one thing is when n goes up, okay, the variance of the sample mean goes down, right? And that means that when n's getting larger and larger, the variation of sample mean reduce, so the sample mean you get is getting more accurate. And remember, the variance is mean the variation around the expectation, right? So it's mu, and then the sample x bar is between the mu and when the variance strength, so that means the variation strength. And then n goes to infinity, that actually become very small, right? So that actually gives us the law of large number. And we also know when the sample size is large enough, then it is like the bell curve. It's like it's like moving around, but it will look like a bell curve, right? That is the central limit theorem. And do note that the central limit theorem, put us the variance of the bell is like this guy, right? This is what we have, right? Central limit theorem means this, right? When n is big enough, okay, that is a good approximation, right? And it rely on the fact that we know the sigma square, okay? And if we don't know sigma square, we need to use what we learned topic 1, use S square, right, to replace that guy, okay? And turn out to be this, okay, you replace by S square, right? this guy, right? I mean, just this is just mean this, right? Just to remind you, okay? This is just Z, right? CO1. And this, under this case, we know if we assume normality, actually just assume the population is also a bell curve, right? The population is also a bell curve. And in that case, this is equal to Tn minus 1, okay? And that means that it's like a bell curve, but a more compressed, sorry, not compressed, it's not more spread out bell curve, okay? If bell is like the red one, okay? If you have the bell, the standard bell is the red one, the green will be the T, okay? So that is the main thing we cover. And a special case we also talk about is the binary data, okay? If data are just CO1, okay? In that case, this is a Benoni, okay? And X bar is actually a transformed binomial, okay? But we in our class we will just use the against the bell curve, okay? Because it's a binomial, then it can be approximated by a bell curve when n pi and n1 minus pi is bigger than 5. In that case, we can use bell curve, okay? And the good thing about this is we need not worry about the S, okay? The reason is being later you will see we can just use this to as estimate, right? As sigma square, and this guy we can estimate, right? So different from the general case, right? Mu and sigma are separate, right? So that's why you have some problem, you have to go to T. But when we talk about proportion, we don't have a trouble because when we have the sample proportion P, okay, we can just go ahead, okay, and do the replacement, and that allow us to do everything we want, okay. So that's basically what we covered last class. So that these knowledge actually we don't use by themselves. Actually, we use in the estimation. So don't worry, all this thing we just covered, we will be using it now in the next class. Okay. So basically, estimation and the hypothesis testing, we will keep using this information again, again, and again. Okay. So that would not be any issue. I mean, this is the baseline basis of what we are going. Okay. So that is why this chapter is important, is because everything from now on will be based on this, except the F, but mostly almost everything is based on this. This slide is a foundation of what we are going to do. Okay. So I hope there should be any question. If no, then we go to the next one. Okay. This slide I just add them because I figure out that this is a good way to summarize the structure of what we are doing in this topic, because I feel like that this is a good summary of what we are doing. Okay, is there a question? Then you will understand why we study this, because today we study one application. The first application is called estimation. Okay, we will try to study how the X bar would behave, because we just learned how X bar behave, right? So we are trying to do estimation. What's the goal, right? Because remember, what we want to learn is mu. Okay, so the main idea is, again, go back to the beginning, is with population here. Okay, suppose you want to know the income of a city, right? A business application is you want to see how much money people have, then you can decide your pricing, or you ask people how people willing to pay for your product, so on and so forth, right? The problem is you're never able to ask every single individual there, right? You want to estimate the average, right? Average income, right? or average, I mean, willingness to pay, right? Willingness to pay, or average age, right? Or of average spending, right? Many applications you want to do, right? Or average time to do certain thing. I mean, then marketing research, right? Or average duration of the spend on an app, or so on and so forth. I mean, average, the meal is very important, right? Because it's a meal, right? This is something I'm going to study, right? Because you learn from topic 1, right? How to, the best way to represent the data. One of the way is look at the mean, right? The average. So we want to know the average. And as we just hint in the last topic, right? We would use the sample mean to try to guess what is the meal, right? So that is the main goal today, okay? We're trying to see, okay, why and how we do estimation, and we try to explain why sample mean is a good way, okay, to estimate meal. And the other thing we want to show is this sigma square. Okay, there's 2 things we want to estimate, right? The first 2 elements that we want to look at. We'll try to do it, but with less detail. We will tell you why S square is good. Okay, why we would want to have square over n minus 1 is a good thing. Okay, instead of the n, right? This is the formula, right? So why we want to divide by n minus 1 instead of n. Okay, so that is the first 2 things we want to say why this is good. Okay, why these 2 are good. And the next thing we want to talk about, today we will talk about what we call interval estimation. Okay, and we focus on X bar. Okay, so the main idea is being that we are talking about, we want to estimate the meal. Okay, and the fact that we have collected data and calculate sample mean, okay, it just gives me 1 number, right? It doesn't, you actually don't tell us the precision of this, right? If I have many data, I have small number of data, as long as they give me the X bar, right, I would have the same outcome, right? So it doesn't give me the precision, precision, right? The problem precision, right? So how accurate we are based on the data, right? So it doesn't give much variability like the variance concept. So the interval estimate is trying to, instead of making a guess of a single point, we put a interval of guess, right? Just like if you try to ask people when they go to the look at the TV and look at the financial analyst, right? They ask, okay, what would be in the morning? They ask, okay, what would be the stock index today, right? The Hang Seng index, okay? They will say, okay, the stock index will be exactly at the end of the day will be 16,500, right? That would not, you not hear like this, right? They will say, okay, the minimum will be 16,000 to 17,000, right? Something like give a range, right? Give interval. So that is we are going to go into the interval estimate. So that's the second part of this topic. Okay. So to recap, so the first thing we look at how we do estimate. We talk about the mean and the variance, and the next part we talk about how to do estimate on the sample and the population mean. Instead of talking a point, we talk about an interval, right? The idea is like the following, right? Okay, instead of a gun to shoot a point, okay, you actually got an RPG, right? A grenade, and then bomb to hit the whole area. Okay, so that is the main idea. Okay, instead of hitting a sniper and hit, right? You just use the rocket launcher and then hit the whole area. okay, bomb, and then you kill every guy there, okay. So that is more or less like this. Is that clear what we are doing? I hope it's clear. What we're trying to do is do estimation, and that's why we learn the sampling distribution is because the sample mean is the main key thing we are doing. Is that okay? Okay. So I hope that is clear what we're trying to do today. So let's have some terminology here. So in case you read the book, they would call the following, right? So we'll call population parameter, okay, or the parameter is something we're interested, say the mean, the variance, okay, and actually mu and sigma square for our case, right? And that are the two things we estimate in this class, okay. That is the two things we interest in. Estimate how average income of the population we want to study, or the variance, okay. And we know from topic 1 that the two important things we want to study, okay. And the two terminology again, which is estimate and estimator, okay. These are just a simple terminology. Estimate is a number, okay. So if I sample data and say I use the sample mean, the number, say number sample, I calculate the data is 10, okay. The number 10 is the estimate, okay, is the number, okay. Estimator is the method that you arrive at estimate. Say sample mean is the estimator, right? Because sample mean is adding up the number and divided by n, so it's an estimator, right? And usually look at the book, they will have this subscript n because it depends on n, right? Because sample means add up the data divided by n, right? So it's depend on n, so that's why it's called the head. Usually the estimator with the head, and if you have an interest, you have a theta. So these are all the standard terminology, not invented by me. Is you read the textbook, this is the standard thing you will see. So I just put it there to make it clear, okay. And technically, right, because estimator rule, right, is a rule that depends on sample. So this is a random variable, okay. Don't notice a random variable because it depends on what kind of sample you drawn. I mean, you learned that in the last chapter, right? And depend on what kind of sample you drawn, right? And estimates the particular value of the estimator, okay? Just to trying to show you, okay? And go back to the previous slide, previous topic, the slide previous topic, right? So we have this, right? 1, 2, 3, right? Remember this example where young man and young girl and old man, right? And if you one estimator is just basically I just draw one number there and that's it. That's estimator, right? And the estimator actually turn out you have, if you actually draw the guy, actually one will be the estimate, okay? And if you draw three estimate, okay? Another example, if the estimator here I have drew the sample mean, which is actually this guy. This is the estimator. Estimator is a method that you arrive at your estimate, okay? And the estimate depends on what actually you drawn, right? If you draw 2 and 1, your estimate is 1.5. If you draw 3 and 2, the estimate is 2.5, okay? So that is the estimator and estimate. I hope that is clear. Is that clear? Estimator is the rule that you arrive at your estimate, right? Your guess. And estimator is a random variable. That's very important to remember. Estimator is a random variable, okay? It's a random variable. Depends because it depends on what kind of drawing. Is that clear? Is that okay? Okay. So sorry for terminology because that is what's the standard textbook they use. So I just kind of make it trivialize it, okay? So as I hinted at the beginning, there are two ways to do, right? And the first one is point estimator, right? And as I said, this is like a gun or sniper, right? You just hit one point, doop, Okay. And the interval estimator is a, I don't know how to draw, but something like this is a rocket launcher, and then just boom. Okay, just hit this area. Okay. So the point estimator gives you one single number, and interval estimator actually give you interval, right? Just like shotgun, boom, right? You hit bra. Okay, is that clear? Okay. Is there any question? How we distinguish between the two? Because okay, I hope that is clear. Although, okay, now we start with point estimator, and then we have interval estimator. So in order to justify why we use X bar, sample mean, and also the sample variance, we need to look at what are the good property of a point estimator, right? What are good property of gun? So first is unbiasedness, second is efficiency, and third is consistency, which we will make clear one by one. Okay, consistency actually a little bit more advanced concept. It related to a limit, but I hope we can make it clear. Okay, so unbiasedness is very simple. Okay, it's very simple. It only means the following: very weak property. It just means that on average we hit the target. Okay, say the expectation is hitting the target. Okay, it can mean that we miss the target all the time. Okay, so look at the graph next. It's easy to look at the graph. Okay, here I have an estimator that can end up with 3 different values. Okay, and this is no way it hit the target, right? It hit end here. Okay, you will say this guy, if they shooter, then it's a very bad shooting technique. Okay, but on average, he's hitting the target, right? So that is unbiased. Okay, it doesn't mean it hit it, but on average, it hit it. Is that clear? So it doesn't mean they hit it. They can never. It can be not anywhere close. Okay, but it hit here, here. The average is here, right? So on average, hitting target, then yes. Okay. Another example we can imagine. Let me draw it. Right. Suppose another example is if you hit here, you hit here, you hit here, you hit here, you're still unbiased, right? Because although don't hit the target, averaging them is hitting the target, right? Another case is like, okay, suppose a number line here, number line 2 here, okay, and there's something on the hit, okay, and I can't hit it, but I hit, say this is 1, this is 3, okay, I hit here once, I hit there twice. Also, I on average hitting target, right? If I hear 1.5 and 2.5, okay, it hit these 4 points, okay, on average also hitting target, okay. So it's very weak requirement, okay. The weak requirement is asking on average is hitting the target. Is that clear? Okay, is that clear what we are requiring? Okay, of course this is weak, but this is the basic thing we require, right? So it's on average is hitting, right? So I think we explained in the last topic, right? We have shown one thing, right? Average is hitting the target, right? The sample mean, okay, of a simple random sample, the expectation is actually the population mean, okay? So that's why the sample mean is a good, it's an unbiased estimator, okay? Is that clear? Is that okay? So on average, hitting target, but doesn't mean that they will hit the target, but just on average. Okay. Now, of course, you will ask, this is very lousy one, right? Quite lousy. You don't really like it, right? And the second thing is, okay, we want it to be less lousy, okay? So how can we do it? It's called efficiency, okay? So efficiency is focused on one thing which is very important. We focus on unbiased estimator, okay? We only compare the two estimator that's unbiased, okay? On average, they're hitting the target, okay? So the question would be like, okay, A is more efficient if A has smaller variance, okay? The variance smaller, okay? So variance of A is accuracy of the hit, right? Is how accurate they are, is how much different from the mean, right? Because they're unbiased, on average hit and target. So it means that the error of A is less than error of B, right? This is error, right? Error of A is less than error of B. Okay. Is that clear? Because it's unbiased, the variance is exactly the error from the mean. Okay. So let's see the graph and explain why this is what it is. Okay. In this case, okay, A and B, this is A, okay, and the blue one's B, okay. It is very clear that A and B are both unbiased because the average is in the middle, it's under B.B.A, right? And you can see A is more closer to the center than B, okay? So we say A is more efficient than B, okay? Now, probably you would ask why we require efficiency. The reason is being like this, okay? Is suppose I have another estimator C, which is something like this. Okay, so this one actually has very small variance, right? It's very focused on a point, okay? But this is not hitting the target, right? So how can you compare A and C? It's not that clear, okay? Of course, there's some way to do it, but in our framework, we are unable to compare the two, okay? So we only compare if they are on average and target, right? We cannot tell A is better or C is better. We cannot, right? You cannot tell it's better or less, or I don't know. I mean, of course, you can. There's some way to do it, but for our purpose, we don't have. Okay, and the reason why we don't need to because we don't have to. So that's why we don't need to learn what are the way to do it. Okay. So we learn efficiency. Okay, we learn unbiasedness. Okay. And the last thing we want to learn is that okay for the efficiency? Okay. The last thing we'll learn is a little bit more trickier, but it should not be an issue. It's what we call consistency. Okay, consistency. The technical definition is very complicated. Okay, but the idea is very simple. Okay, try to give yourself a math idea. What it said is the following. I just bisect this guy slowly, then you will try to understand. So this is what the estimator, right? And this is what we're trying to guess. Okay, the theta is the one to guess, right? This is the theta is the B.B.A, right? The target. Okay, and if we look at the difference, okay, is how far they are apart, right? And you look at the absolute value, right? Look at how distant they are, right? Look at the distance, the absolute distance they are, right? So it means that the larger they are, the worse is it, right? You want to be as little as possible, okay? So if I give you any number, okay, whatever number it is, okay, I want this number bigger than a small number. I want the probability is very small, right? It's very small. At the best case is I want it to go to 0 if my sample size go to infinity. Okay, so that is what it means. I repeat what we're doing. In this statement, it said this is our gun or weapon, okay? Or this is our weapon, okay? And this is our target, okay? We want our weapon hit the target, or we want it to miss, okay? The distance between them, the inaccuracy, the error, actually this is error, right? This is error. Okay. Bigger than a certain number, okay? Any number you make, okay? Any positive number. The probability bigger than a very small number should be very small, right? And we only care about when we have very large sample, we want it to be go to 0. Okay, so basically is that if I have large enough sample size, I will hit the target. Okay, that is what he said, right? If I have larger and larger and larger sample size, eventually the target is being hit. Okay, so it means the following, right? So if I am a soldier, right, I use a small pistol. Okay, this is the target I want to hit. Maybe I hit the target here. Okay, maybe I'm not so good. Okay, somewhere here. Okay, and suppose I increase the sample size, right? Then means what? Means maybe I improve myself. I have a bigger gun, right? And I hit a closer. Okay. And now instead of AK-47, right? I have I don't know, I have a machine gun. Okay, machine gun. Okay, and I hit closer. Okay, and it can be anywhere, right? Maybe somewhere here around, right? It may not be unbiased. Okay, maybe biased, but doesn't really matter. At the end, I have a laser gun. Okay, it will pew hit the blue eye. Okay, that's what it means. Okay, it means that if I have a better and better gun, I will actually hit it. Okay, I improve my technology, which means that I have bigger and bigger end, right? So let's see the diagram here to get a more easier shape. Okay, here initially, okay, I have a small sample size 1, right? And the midpoint may be here. Okay, it's not biased, it's not unbiased. Okay, it's biased. It's a bias estimator. Okay, on average hitting somewhere, not hitting the target. Okay, and the second one, I have a better gun, right? I have a AK-47, not a pistol. Okay, but still it's not hitting the target. Okay, but it's getting closer. Okay, and I have an laser beam. Okay, and it is getting closer. Okay, and if I keep increasing and go on, it eventually hit what we want to hit. Okay, so that is what we call a consistency. It's like if we improve our gun, okay, and we will hit it. Okay, it's not unbiased. Unbiased is on average hitting it, but here consistency means we actually hit it. Okay, so when n goes large enough, so that is what we want. Someone asked why theta 1. Okay, because the estimator, okay, can have 3 different values, right? Depends on what sample you're drawing. It can be here or here or here. Is that clear? Ricardo? Because theta 2 is here means you have sample size of 2, can end up in the 3 red dot. 2 is the subscript. Subscript is a sample size. Okay, so you can, because depend on sample you drawn, can be here. I just illustrate, right? Because it can be many possible ones, but I just illustrate. If you're 3 of them, then you get them. Okay. I hope that's clear. So you know that's a 3 property: unbiasedness, efficiency, and consistency. So we try to evaluate the estimator. We want to know X bar and S square. Okay. So first we want to show you sample mean, right? This is the thing we want to know because sample mean is the first thing we learn, and then also the important part. So here, I'm not going to go to the proof, but it essentially say the first thing is it's unbiased. Okay, it's unbiased. We define it. Okay. The second one, okay, it's also efficient. Okay, and efficient in the sense that if you look at any weighted average, okay, simple average is better than weighted average. Okay, the proof relies on Cauchy-Schwarz inequality, which I'm not going to say anything, but what it means is sample mean is better than any weighted average. That's why we will weight every sample by 1 over n. Okay, so the proof rely on Cauchy-Schwarz, but I mean, if you don't want to care, you just remember two things. One, sample mean is unbiased. Second is efficient. Okay. Third, oh, I didn't say it out. Actually, I should have third point, put a point here. Okay. The third one is consistent. Why? We learned it. This is law of large number. Right? Law of large number said when you increase the sample size, eventually the sample mean goes to the population mean. Okay, so that is eventually, if we collect enough sample, we know what we want. Okay, is that clear? So that's why it's good. I mean, efficiency can be stronger, but I just prove it is better compared to weighted average. But yeah, I mean, is that clear? Okay, so that's why we use sample mean. Sample mean is good. Okay, so that's why we keep using sample mean. That's why someone asks, okay, why don't we use the geometric mean? We don't use harmonic mean. We don't use some weird thing. Yeah, no, we don't, because that is better. Okay, I hope it is clear why. Okay, some question? Still confused with dot. Okay, so just go back to here. Why? So here it means the following. We have an estimator, this guy. Okay, estimator use one sample. This estimator can go to one estimate, two estimate, three estimate, depends on what sample we realize. And this three number will be possible realization of possible outcome. Okay, just like what you learn is X bar. Okay, we have data 1, 2, 3 here, right? And this is data 1 and 2 and 3, right? Look at, remember if set is 1, right? And if you have 2, right? We have 1, 1.5, 2, 2.5, and 3. This is an example from the last chapter. So it looks like it's getting inside. Okay, of course there's some outside as well, but and X3, right? You have even more that actually the variance getting smaller. Is that clear? If you can go back to the is essentially this graph you can translate into all cover here, right? Sample size of 1, sample size of 2, sample size of 3, and the variance actually shrinks. Is that clear, Ricardo? Okay. So I hope that is any question? So we prove sample means good. I hope you agree with me, right? And I guess this is now the time to solve the mystery of n-1, right? Because you keep asking in your head, probably when you learned it in your high school, why n-1? That's weird. Okay, to be honest, I spent huge amount of time to understand n-1. In those days, there's no internet. Okay, actually, I spent the time in the library for I think at least a week to figure out why n-1 when I first learned it. Okay, because there's no internet at that time. I mean 20 years ago, right? 10 years ago, there's not much internet, and you can only look at the books. And I look at almost all the textbook there, and at the end, I figure out why it's true. Because actually, you learn it, you don't tell you, but you tell you in this second half of the textbook. Okay, so okay, then I learned it, and why is it so interesting? Okay, why n-1? Okay, and okay, the thing is, we can solve this guy. Okay, the expectation of S squared is actually sigma squared. Okay, so it means the following. It means that if you want an unbiased estimator, S squared will be the best one. Okay. And okay. So here trying to prove this guy. Okay. And okay. I don't think I should talk about the proof. I guess everyone would got sleep if I go over the proof. Okay. So besides unbiasedness, okay, and can I do efficiency or consistency? Okay. And I do not comment on efficiency, but I would comment on consistency. This is also consistent. Okay. This is also consistent. Okay. And probably you want to ask if I have 1 over n, okay, and this is actually consistent as well. Okay. So that's why when you use n, it's not a big deal sometimes, but the only difficulty is this is not unbiased, and we prefer unbiased, right? Because unbiased means that you have the meaning of unbiased is no reason to believe that it's more likely than that or less likely than that. There's no it's not likely to be overestimate or underestimate. Okay. So that is the reason why we want to do that. And I guess no one want to look at the proof. Then I just, because the proof is a little bit involved, I just left it. If you want to know what's going on, I can help you, but I guess no one want to do the proof. But the proof involved is like you have to prove this, involved in this crazy item, and then you have to prove this guy, and then go back, you put it in, and then get you the answer. Okay. I don't think you are interested in looking at the math unless you really want me to do it. If you want, then I can. If you are stuck at some steps, you can ask me, or try to look at the textbook, or which gives you the proof. Okay. So before I end, let's go to this very special case. Okay. A binary data, right? I think I mentioned that the binary data has with the same, there's no difference. Okay. There's some question again. So what's degree of freedom? I don't have degree of freedom in this one. Okay. And degree of freedom only in terms of T distribution, we talk about degree of freedom, but here we don't. There's no degree of freedom here. Okay. So we will talk about degree of freedom, we'll talk about T distribution and F distribution, and that time probably we will come back and comment on what degree of freedom is, but at the current moment we don't. Okay. So probably we go to the T distribution later in this class. We'll talk about those. Okay. And so let's finally talk about the proportion. I remember we talked about the binary case. Sample mean in this case is a sample proportion, right? So by what we have just discussed, because sample means a sample proportion. So sample proportion is just an unbiased estimator, have a good property of efficiency and also good property of consistency. So sample proportion is good. So I don't need to say further. Okay. And as I said, it's unbiased, right? And the difficult part is the sample variance. Okay. We will use this guy. Okay. Because this is the sample variance. And one of the way to estimate is just this guy. Okay. P times 1 minus P, because pi, right? Expected P is just pi, right? So we probably want to plug in this guy there, right? And that is our estimate, right? It's very natural to do it, right? Because pi just expect pi, the population proportion is just sample proportion, right? So the variance, you can just plug in, right? It's very natural to think that is the case. Okay. Unfortunately, this is a bias. Okay, this is a bias, but we still use it. Okay, so it's a bias, but we still use it. The reason is the two reasons behind. One, as I mentioned, this is still a consistent estimator. It's still consistent. Okay, this is consistent. Okay, but it's a bias. Okay, and why still we use it? Because it's convenient. There are other property that is desirable, and also look at binary data, and tend to be large, right? Because later you will see. Let's go to the next slide. Okay, the unbiased version is like this. Okay, if you do this adjustment, this guy become unbiased. Okay, but the good thing about proportion data is usually you work with a n is big enough, right? You look at proportion data, usually at least like several hundred or even thousands. Okay, and usually that is a problem, right? Because thousands or 100, you take n over n minus 1, usually it's very close to 1, so that's not easy. Okay, so do look that you have this one. That means that the original one, okay, this one, what you have is you would underestimate the variance. Okay, same as the idea here, right? If you calculate this guy divided by n minus 1, right? If you calculate this, okay, and you calculate divided by n instead of n minus 1, actually you are underestimate, right? Underestimate the variance. Okay, and maybe before I end, maybe okay, then that means that, as I said, we have you can replace this. This is the sample variance and the sample standard deviation. Okay, and maybe before I end, I just probably get to someone actually asked the degree of freedom. Okay, and I can kind of explain why M-1 is related to, I mean, like Ricardo said, related to degree of freedom. In the following sense, why this is an underestimate. Okay, why did underestimate? The reason is being that we need to estimate this guy. Okay, we need to estimate X bar. Okay, once the reason why M-1 is because once I estimate X bar, okay, the main reason is if I have data X1 up to X2 up to Xn, okay, I use the data to estimate X bar, right? And when I calculate the variance, right, I calculate the difference between each number and X bar. Okay, the problem is X bar comes from X1 to Xn, right? So when I calculate up to Xn minus 1, okay, I do the calculation X1 minus X bar and do all the summation, right? I add up to here. Okay, the last one, actually, you know the answer, right? Because if I know this guy, I know the first n-1 guy, the last one is getting known, right? Let me repeat the statement, because the X bar is the estimate, right? So that's why if I know all but the last one, actually the last one has been fixed because I know the first n-1, I know this guy is fixed. So you calculate the variability, actually it's one less because you estimate this guy. Okay, so that's why well, that's why they call degree of freedom is because there's no freedom to move this guy. Okay, only the freedom is the first n minus 1 because the last guy has been fixed. So that's why a lot of the introductory textbook would say, okay, why n minus 1? Because actually you don't have n guy to vary, only n minus 1 guy. So the degree of freedom reduced by 1. So this is how they come up with this explanation. Ricardo, are you happy with the explanation? Okay, so I guess we're break. So we just finished the point estimate. We know how to do estimation. So after the break, we'll talk about interval estimation. Okay, so I go around to see if you have any question. In case you have any question, the Zoom is just type. Otherwise, other people can I go around to check. So I have a question from the X bar taken from Xn. X bar is just X1 up to Xn, right? X bar is just X1 up to Xn divided by N. Is that okay? So your text data, I sample 2 each time. I sample 2 each time, so I get 3. Oh, you can have more than that sample. You see the no, because if you look at this, you can have many cases. The data you draw from population means they are fixed. I'm not sure I understand your question, but the population is fixed, but the sample you draw depend on randomness. I don't know it's clear, but I mean, if you see a question, maybe you just email me because I'm not fully understand this. Okay. So I guess we resume. There have been quite a few questions, so I just answer most of them. I hope that would be clear. So I hope it's clear because these things are a little bit new. I mean, we have a lot of new terminology that try to cram it in 1 or 2 classes that have to be, you must have some theory because that's not easy concept, as I said, okay? But in case you're still confused, just keep asking me. I mean, it's okay, so don't worry. And if you do the assignment, if your question arises from the assignment, although I can't answer directly, but you can still ask me the material in the text, Okay, but you become more clear when you do the assignment. But I hope. Okay. So I hope it's okay. I mean, if Ricardo, I mean, just if you still confused, you can just talk to me later or just email me. Okay. So now, as I said, we just know how to shoot one point, interval estimate. Instead, talk about shooting multiple points. Indeed, you a shotgun and hit whole area. Okay. Just an atomic bomb and bomb the whole area. Okay, it's go nuclear. Okay, so how to go nuclear? Okay, and is that we need to know how X bar looks like. Okay, we need to look at how X bar looks like. Okay, how X bar behave. Okay, without no X bar, then you can't really do anything, right? Because what we say is, okay, the following, right, is what we learn is we want to hit this mu, okay, and we have X bar, okay, but we don't know where X bar. X bar can be here, X bar can be here, X bar can be here, can be any point, right? We just know on average it hitting the target, and when the sample size get larger, they will eventually hit it, right? So the consistency is here, but we don't know when n is not infinity, right? So the question is how we want to look at how X bar looks like, right? So what we learned last class is one thing is central limit theorem. It's the following: X bar here and mu is here, right? And we have this guy, okay? So we learned this is one thing, we know that property. So we'll use this property, okay? We'll use this property. So we'll use this bell curve to do our analysis, okay? What we are trying to do is you use a shotgun to, instead of this guy, we will try to say, this guy, this is our guess, okay? Or this is our guess, or this is our guess, okay? So basically, we are trying to do is from this area, we just go around, okay? That's why we say a nuclear bomb is, we know this point, we want to shoot, okay? We're not going to this point, we go all this point around it, okay? And how do we decide how big is the bomb we are going to use, okay? We need to rely on how mu and X bar are related, okay? That is required on how what is the distribution of that, okay? So rely on either central limit theorem, this will give you the bar, okay? And the second one we can rely on is we rely on normality, okay? By normality, assumption is the population, okay? The data also follow the bell curve, okay? So if everything in the original data is a bell curve, this is also a bell curve, okay? So let me repeat the statement. If we want to do a nuclear bomb, okay, we need to know how X bar and mu related, right? And we need to know how they look like in more detail, okay? And it is in bell shape according to central limit theorem. This is whole when n is very big, right? When it's big. And when n is big is, we mean n is bigger than 35, okay? It will hold, and the bigger the better, right? And the other way to justify this is we start with a bell curve, and then we also, the sample mean is also a bell. Okay, is that clear what we are heading for? Okay, if that's okay, then we will try to explain what we are doing. Okay, the main idea is, as I said, we want a symmetric interval, okay, to such that with some probability that will include mu, okay? What are we saying here? Okay, what I say here is the following, okay? Is the fact that go back to here, okay? This is a bell curve, right? So what we want to do is we would end up, if we draw a sample, we may end up here, right? Suppose this is our sample, we draw this line, this is our sample, okay? And this is our point estimate, okay? And we actually want a nuclear bomb, right? So we will go left and go right. This will just bomb, right? We just have a rocket to bomb here, right? Bomb this whole area, okay? So that's the idea. Point estimate, we just get the data. This will be the point estimate, right? Now we go left by M, go right by M, okay? And of course, we know that, okay, this normal distribution is infinite, right? Go to the bell curve, never ends, right? So there's no way you always include, right? So there must be some probability, okay? No matter how big is the M, right? As long as finite, you cannot cover mu, right? That's possible that you go away. Never repeat the statement. Because normal is you go the 2n, right? So you can end up the sample mean will be very, very large or very small, right? So unless your M is infinite, right? There's some probability you miss it. Okay? The reason is because you may end up in very far away, right? There's some probability end up in far away, right? Because it's normal. So that's why what we're trying to do is we would say what we're trying to do is the following. Okay, we're trying to say is, okay, the probability you include the mu is 1 minus lambda. Okay, so let's go back to here. What it means is the following, right? We draw this, we go M each side, okay, and we will have 95% include the mu. Okay, that's what we're going to do. Okay, now that before we do the thing, we try to say we do it, go left right by M, 95% we will include mu. Okay, okay, is that clear? The statement is, again, it's very careful, is we want a M, okay, such that if I add and subtract from the sample mean, just go left and right, it will include the mu with probability 1 minus alpha. Of course, later you will see alpha is very small, okay? So that is the goal, okay? So before we prove it, actually it's easy to prove, but we try to prove it, later turn out to be M is this guy, okay? This is the formula that you will always remember, but don't worry, this will be the thing, okay? We'll try to prove this is what we want to do, okay? So we will try to tell you what is the size of the nuclear bomb. It's just this guy is M, it's called this guy, okay? We'll prove this is the case. That will not be difficult, but we'll try to prove it, okay? So that is what we're trying to do is, this is our point estimate, and this is our range, okay? So basically, look at this graph. Is look at this bomb here, X bar is here. This is the M, right? Or M is here. M is defined as Z alpha over 2 sigma over root n, okay? Which we will make it clear very soon why this is true, okay? But let's, okay? The proof is actually not that difficult, okay? The reason, maybe I forget about, let me draw it out and like maybe prove this guy why this is true, okay? This, okay, we have here, mu is here, okay? And what we want is, we want to draw this guy, okay? And go left by M and go right by M, right? And right, it will include mu a lot of the time, right? You include mu all the time. So we want this let me write down the bottom. So proof is like this. X bar minus M mu X bar plus M, okay, is equal to 1 minus alpha, okay? So how can we proceed from here, okay? And do note that mu is a unknown, it's not random variable. The random variable only appear in this guy, okay? Okay, this only random variable, okay? Let's focus on the right hand side, okay? Mu is less than X bar minus M, okay? Of X plus M. So let's do the following, okay? We move X bar, we move the M to the other side, negative M. We move mu to the other side, negative mu. Is that clear why we do that? Is there clear why this is true? Is that clear? Okay. And next step is I over sigma over root n. Okay. And why I do that? Because this guy is standard normal, right? Z. Right? Z is bigger than. Okay. In the other words, I actually convert this to a Z. Okay. This is 0. Okay. And I want, okay, look at this side, is I want Z is less than this guy. Okay. And you can see here, if plus M here, I change to minus M, right? I can do the same for the other side. So I can do mu is less than X bar minus M. Okay. Let me do this. Okay. And I can rewrite this to mu minus over M. Okay. And I do the same thing here. I have X bar over root n and M over, oh, where I am? Okay, over sigma root n. Okay, so it's like Z is less than M over sigma root n here. Okay, so this statement, okay, is actually replaced by Z is just this guy. Probability that Z is between, okay, negative M, this guy here, over sigma over root n, and this guy here, M over sigma over root n. Okay. So what does that mean? It means this, right? M over sigma over root n here. This is negative M over sigma over root n. Okay. So what I'm doing is I transform this thing. Okay. I transform this statement. Okay. Into the statement of the standard bell curve, where it's between these two values, and I want this value to be 1 minus alpha. Okay, so there's a math here. Okay, so if you don't follow the math, that is the idea is the following. I just look it here. Okay, let me do it here. Is the following. Okay, just let me redo the thing here because it's very important. Okay, so what I do here is, okay, so this is the question. Mu is uncertain. What I want is this guy. Okay, X bar. I go left by M. I go left by M. Okay, so this is X minus M. This is X bar plus M. Okay, the question is, I want this guy. Okay, mu is between X bar plus m, x bar minus m is 1 minus alpha. Okay. So the math I have done is trying to show you this. Z here. Okay. This is 0. And I can transform this into, I want this 1 minus alpha. And this is just m over sigma over root n, negative m sigma over root n, by using the fact that x bar minus mu over sigma over root n is actually z. Okay. Basically, you rearrange the inequality. That's what you get. Okay. So that actually what you get is z is less than, right, m over sigma over root n, m over sigma over root n. Okay. This guy is 1 minus alpha. Okay. So that is the goal. Basically, it's just like asking x bar go left by m. You would include mu with probability 1 minus alpha can be rewritten as the following. Asking the sample mean, the normal, the z is actually between this area, okay, with the m. Okay. And if we recall, okay, this is symmetric. Okay. If this is 1 minus alpha, this guy is alpha over 2. This guy is alpha over 2. Right? And we learn the notation. If this is alpha over 2, okay, this line we call z alpha over 2. Okay? So that's why we have the answer. M is just z over 2 times sigma over root n. So this is the proof we have. Okay. So it just, there's no particular math here. Basically, just this is what we want to start with some inequality adjustment, end up with this guy. Okay. I hope that is, I don't know whether it's clear or not, but that's the proof. I mean, also I have a more cleaner proof in the slides. Okay. I think of course, as I want to emphasize that the proof is not important. Okay. You only need to memorize. I mean, you just need to know this guy. Okay. That's the key point. But what I try to do is to try to show you what actually we are doing. Okay. It's just saying that our sample mean can be any number. Okay. Along this bell curve. And I go left by m, right by m. Okay. And I want this thing 95%. I mean, 1 minus alpha probability will include the mu. Okay. And how can we proceed here to here? Okay. The thing is, we can transform this inequality as we just done in this line. Okay. We can do left and right. Okay. That ends up in this guy. Okay. And that is how we get this formula. Okay. Or if you don't like this idea, the simplest thing you can think of is, okay, is because it is considering the other way around. If you think, is the following, right? This is a, sorry, here. Okay. The other way around to think is like this. Okay. This is x bar. Okay. Instead of making like x bar go left m, okay, whether you will include the mu, you can think in the following way. You can think alternatively. Okay. This is the mu. This is the bell curve. Okay. You can think the following. Go left by m, go right by m. Okay. And actually, you're asking you how long extend such that the x bar is belong to this range. Okay, let me repeat the argument. The argument is saying that X bar go left by M, go right by M, and that will include mu, right? But the same, right? This include, you go to X bar, you touch it, whether you touch the mu, right? Go there, right? But you can all look at whether the mu, whether you touch the X bar, right? So the X bar is, if X bar is within this area, you'll be touched, okay? So that's why when you, the idea is like you transform this to Z, right? And this is same as 1 minus alpha, this is Z alpha, right? So this guy must be, if you transform this to here, right, will be Z alpha over 2, right? Z alpha 2 times sigma over root n, right? Because this is sigma over root n. You just go here from here, you just like this one, right? So that is the same. This is another way to think quickly, right? Because X bar whether include mu by extending the M is same as mu go M left and right, right? So either way you think it's the same thing. Okay, is that clear? Is that clear what we are doing? I mean, it's rather convoluted, but I try to give you 2 reasons why this is true. Okay, one is actually working on the math to get the solution. The other is just use this idea of you catch me and then the same as I touch you, same as you touch me, right? You touch X bar go left and right by M, it's same as mu actually go left and right. And as long as X bar is fall within this range, then the same thing happen, right? As long as X bar fall within this range, then same as you go left by M, the same thing. Is that clear? So that is the idea. Is that clear? So if, okay, so that's the idea, okay? So that is what we call the confidence level, okay? And there's some terminology here. The length of this guy is called margin of error, okay? That's M in our previous slide, okay? And this is the length of the arm left, right? And left and right add together is called 2M, is called the width, okay? And there's LCL and UCL. LCL is the lower bound, upper bound, okay? So just like this is X bar, okay? You go left by M, go right by M, okay? And this is called W, okay? And this is X minus M. This is LCL, right? Oh, sorry, LCL. And this is X plus M is UCL. So the question from the yeah, because alpha, we define alpha in, I think in the topic 3, how we define alpha is like this. Okay, we define this alpha and this will be Z alpha. Is that clear? So you define at the right tail. Okay, and because of the fact that the center is 1 minus alpha, and these two add up, it must be alpha, so that's why alpha over 2, alpha over 2. Okay. Okay, so I hope that is clear. Okay. I mean, I'm pretty sure that it's not immediately clear. So let me try to draw a graph to see, okay? So you can, this graph I think is very, very intuitive. So Z is here, okay? And C is here. So the sample mean is looks like this bar graph, okay? And it really depends on what kind of sample you get, right? This sample is 1, the sample means 1. Then you can go left and right, okay? And in that case, you include the mu, right? If here, actually it doesn't include. If you, in this case, you include. In the green, you include. The blue, you didn't. You also include. Okay, so that's the idea. Okay, let me repeat the statement because the sample mean actually follow the bell curve, right? So we're likely in the center, right? But if you are at here, you draw the arm left and right, you include 0, right? Green, you also include the 0, and this will include 0. Okay. So that is the guess. Okay. Don't remember how will you get is you guess is negative 1.5 and the range go from here to here. Okay. Is that okay? Now, maybe it's good to have example, then you will see what we're actually doing. Okay. So we start with population is 4. Okay. So probably you ask, okay, how can we know this is 4? Okay. We'll talk about the case where we don't know sigma. Okay. We don't know sigma. Okay. Now, the question is following. Okay. We have the sample with N64 and sample mean is 3. Okay. So, okay. So let me repeat the question here is, I have a population here. Okay. I want to know the sample mean, which is no idea. Okay. No idea. Okay. And I know the sigma is 4. Don't ask me how I get this one. And I usually don't know. Okay. We talk about how to do if you don't know. Okay. We just assume we know for the moment. Okay. And what you're doing is you have to draw 64 sample over here. Okay. Draw 64 guy there. Okay. And you calculate, say, x1 up to 64, right? So you have 64 data. You calculate the sample mean. The sample mean is 3. Okay. So 3 will be your point estimate. Okay. You have a gun, you shoot. 3 is what you guess. Okay. You want to guess mu. 3 is the guess of mu for you. Okay. So what you want is you want to guess more than this. How you do it? What you do is you construct a 95 interval. Okay. 95 standard thing. So alpha is actually 0.05. Okay. Alpha is 0.05. Okay. And you can look at the set table. They give you this answer. How can you do that? If you can do it, it's called norm as this. Oh, sorry, it's not this. It's norm as inverse because you said reverse it. Inverse, okay. And inverse actually gives you the left-hand side. Okay. So the left-hand side is 0.975 because this is 0.05 divided by 2. Okay. Alpha over 2, right? Alpha is 0.5, so it's alpha over 2. Okay. Is 0.025. Okay. So it's 0.75. Okay. This is Excel entry. Okay. So once you have this entry, you put in the formula, which is Z sigma over N. Sigma is 4, N is 64. Okay. So you end up in this 0.98. Okay. So basically what you get here is you estimate 3. Okay. You basically go left by 1, go right by 1. Okay. So basically the guess is 3. The lower bound is almost 2. The upper bound is like 4. Okay. So you just like everything between 2 and 4. Okay. That is your guess. Is that okay? I mean, I'm pretty sure you have some confusion. Okay. Don't worry. We'll continue to talk about that in next class. We're repeating this one. Okay. So don't worry. Have a nice weekend. If you have a question, you can just wait outside to answer. Okay. So thank you. Bye bye.